Well, now we're ready to talk about the synapse. And I want to make sure you know that we're going to talk about a chemical synapse. This is a type of junction where a chemical is released across a gap. And we're going to show you this diagram. But I want to make sure you know I'm talking about a chemical synapse. Okay, so let's enlarge this. And I'm very thankful for all the medical illustrators out there that can draw great things that I cannot. And again, I'm going to point out some main characteristics of this synapse, and then of course you can always have the pause button to read other things that I might ignore. I don't want you to maybe ignore anything, but you can read things on your own. Okay, first of all, there's this thing called the action potential. And you probably should also know that another name for this is a nerve impulse. And these things are unidirectional on any given neuron. And if you remember, the fundamental is the axon is the end of a neuron, and it's the end of the neuron that sends a message to something else. Okay, it's not going to receive a message, it's going to be sending it, we'll see. Anyway, when an action potential comes down the membrane, and we'll be depicting this later, it ends someplace in here, but that is a signal, in this diagram at least, to show you calcium rushes in, and that's a signal for these vesicles to fuse with the cell membrane and release the chemical. And the chemical in this case is called a neurotransmitter. So a chemical synapse releases neurotransmitters. There are many different kinds. But whenever a neurotransmitter is released, it diffuses across this gap between these two membranes. And the gap is called a synaptic cleft. Okay, so the neurotransmitter, diffuses across this cleft, this gap. It binds to specific receptors. And then that is the message for this membrane to depolarize and then transmit its nerve impulse in this direction. So notice how I'm pointing with the laser pointer. This membrane depolarizes and the message is sent down, in our drawing, down along this dendrite. It's called a postsynaptic cell. In many cases, it's a dendrite. But you should also be aware that this postsynaptic cell could be a muscle cell, a myocyte. And we'll be talking about that later. Okay, now I'm going to show you another drawing and an actual picture of one of these synapses. And, God bless the medical illustrators. I have no artistic ability. So let me look here and point out some things in the left part of this big image. This is the presynaptic axon. That means the message is coming down here and it's before the synapse. And you could think of the gap down here as the synapse, I guess. So this is presynaptic axon. The direction of the nerve impulse is always going to be down this way. Sometimes this enlarged area is called the synaptic bouton. So that's a new term. And you know that when action potential reaches the end here, that is a stimulus for the neurotransmitter to be released and diffuse across this membrane. And it's showing specific receptors, and they're calling this the postsynaptic dendrite. You could also call it the postsynaptic membrane. Again, remember, this is another neuron down here then, but it could be a muscle cell. So then, let me scoot this over a little bit and just do this middle part here where it's showing the vesicles that are fusing with the presynaptic membrane, diffusing across that gap, which we call the cleft, binding to specific receptors on the postsynaptic membrane. So this drawing could easily be a dendrite down here or a myocyte. Then finally, the beautiful thing about this whole figure is they're going to show you an actual photomicrograph of this synapse or of a structure. So let me orientate you. Here's the axon terminal. You can see the title up on top. But let me outline the whole axon that we can see. I'm going to start up here. Hopefully you see where I'm at. And here is the axon terminal, the presynaptic membrane right there. Okay? Then that means this lower membrane is the postsynaptic membrane, which belongs to a dendrite in this case. And they're showing the vesicles that would then contain the neurotransmitter, and look how small this gap is. It's not like the artist drawing it where it's very clear and everything, but this is the gap. This is where neurotransmitters diffuse across and bind to a receptor. It's very microscopic, and in their artist drawings, I'm going to go back to it, it looks like maybe it's filled with air, right? You could maybe say, oh, there must be nothing in this gap. Well, lo and behold, there is no air in these junctions. It's actually filled with what's called interstitial fluid. So there'd be fluid here that the neurotransmitter gets dumped into, and it diffuses across a very microscopic distance. And then one other thing about neurotransmitters, once they bind to the postsynaptic membrane, they have two possible fates: to be degraded by an enzyme or to be pumped away from the area, because that's one characteristic of nerve function. Neurotransmitters bind to the postsynaptic membrane, and then the neurotransmitter is degraded or removed. Okay, now I want to show you this great little image and orientate you to the points that we want to make. If the impulses are traveling down here, down in this direction, from the left to the right, then I know over here someplace is the terminus of the axon, where the neurotransmitter is going to be released. But I want to look at some things here. Now, this axon, when the membrane is at rest, and I guess I'll use this one over here, the inside of the nerve membrane is negative relative to the outside. So the outside is depicted as positive, the inside is negative. This is resting, and in this they're saying it's still polarized, right? So at resting, the charges are polarized, and it's minus inside, positive on the outside. Now on the far left, it shows what happens when it's depolarized, and we're going to be looking at an action potential closer in a minute. When it depolarizes, it's a complete opposite. Plus on the inside, negative on the outside. And this shows a myelinated sheath. Myelin is a fatty white substance that covers axons, and wherever it covers the axon, this area cannot depolarize. And this is a very important point. The myelin sheath prevents depolarization. So when there is a message coming from left to right, in this case, this portion of the membrane depolarizes. There's ion movement in the inside of the neuron. There's the inside labeled. And that's a stimulus for this area to depolarize. We got some ion movement, and then this area depolarizes. And the end result is that a myelinated axon transmits nerve impulses faster than if it was not myelinated. These little gaps are called nodes of Ranvier, down here. And so what I wanted to point out is if an axon is myelinated, it tends to transmit nerve impulses up to 10 times faster than if it didn't have myelin. And some of the data suggests that the nerve impulses can travel 120 meters per second. Okay, well, if you're like me, I can understand miles per hour faster, or better, I should say. Although all the scientific literature is in the metric system, so I know why I found that value, 120 meters per second. But my little feeble brain said, how many miles per hour is that? That's the same as going 268 miles per hour. So nerve impulses travel very fast, even if it's half of that value. Even if it's half of 120, say 60 meters per second, that would mean 134 miles per hour. I think you'd agree that's pretty fast conduction. Now we're ready to show you how the electrophysiologists depict action potentials, or you could say nerve impulses. So let me orientate you to this diagram that somebody made. It's perfect, it looks good. Okay, so one point is an action potential, when it's depicted like this, is looking at one point on the membrane only. And if it's myelinated, then it's looking at like a node of Ranvier and depicting what happens. So follow me here now. I'm down here. When a membrane is at rest, it's called the resting membrane potential. Remember, it's going to be more negative on the inside relative to the outside, and that's how this is being depicted. So the resting membrane potential is often minus 70 millivolts. Some diagrams or other drawings will show maybe 90, 65, minus always, whatever. We'll do minus 70 here. It stays at minus 70 until a nerve impulse comes along. Then there's a change in membrane potential. It decreases up to a certain point. And once threshold is reached, that's minus 55. So this line is just showing you where that is. Then you have what's called an action potential generated. Depolarization means going up in this direction. It peaks out at, let's say, plus 35 millivolts, but then the potential is going to be regenerated, so it's called repolarization down here. It comes down. If it goes below resting, it's called hyperpolarization, and we'll talk about that in a little bit. That is one action potential on one spot on the membrane only. Okay, so now let me move this over a little bit because I want to look at this other part of the diagram and talk about hyperpolarization. Now here's the spike, that's the depolarization. It's just crunched up compared to what we had before. If the cell membrane goes below minus 70 millivolts and stays there, it does, you remember the other diagram showed a little bit and then back up to resting. But if it stays there, that means this membrane is less likely to depolarize. Because if you're below resting, you're further away from threshold. Remember, threshold was like about in here someplace. So hyperpolarization means that nerve is less likely to fire. It takes more stimulus to get a nerve impulse sent on that membrane. Okay, so that brings up the discussion about there are two types of neurotransmitters in general. Those that excite the membrane, which means going to cause a depolarization, and those are called excitatory neurotransmitters. Okay, that's not what's depicted here. What's depicted there is the influence of an inhibitory neurotransmitter. And inhibitory neurotransmitters tend to move the membrane potential more negative, or hyperpolarization, and those transmitters then, inhibitory neurotransmitters, would make it less likely for that nerve to initiate a action potential. Now, remember how I said it was on one point on the membrane? And this nice little diagram shows that. So I'm going to cover up some things, that's okay, because this is my focus now. And this diagram shows you if you had three little electrodes and you're monitoring the impulse coming down, because the impulse would be initiated here in the dendritic area, travel along here, and go down, and this is where the terminus is. Okay, so at point A, if we're following this, here's the depolarization, okay? And at some time later, it's going to be at B, but if you notice, there's nothing moving, no peak on this recording because the impulse is at B. So B shows up like this, and at some time later, the impulse is at point C, but this diagram makes a great point of we're recording at a certain point, and after that, it goes back to resting. Okay, so A, B, B. Really a nice diagram. Finally, I just wanted to make the point and add a few more terms here. Remember, this is an action potential just monitoring one point on one membrane. This is millivolts. This is time along the x-axis. Remember, threshold is that point where an action potential can be generated. And this diagram shows that if membrane potential moves towards threshold, but then the stimulus is not large enough to hit threshold, then resting is restored, resting membrane potential. And so here's another stimulus, didn't quite make it to threshold, neither did this one, so it's always a propensity to separate those ions and get back to resting. Now, if you do have a stimulus that reaches threshold, then what's called an all or none response occurs. The membrane completely depolarizes and then regenerates and comes back to resting. So that's an all or none phenomenon, which is very important. It either happens or it doesn't. So in any axon, the amplitude, if you measured it from here, from resting, up to here, it always stays the same. Amplitude is always the same on any given axon. Okay? And then they make a point about a refractory period. That means during this period right here where I'm circling, that means it's less likely or basically impossible to initiate another action potential. So if something's refractory, you can't start another action potential until it reaches to the resting here. Okay, so then one more important point. If you have bigger stimuli, and this I can point out here, remember that's a little stimulus that never made it, a little bit more, but then you just reach threshold. But what if it was this amount of stimulus, but then what if we made more stimulus? Does the action potential go higher? And the answer is no. On this axon, it can never go higher than, let's say, 150. So then the question is, how is the strength of the stimulus recorded? So like, let's say a cat steps on our big toe versus a horse. Well, you know the force that the horse is going to place on your big toe is bigger, larger. And so here's how the nervous system does it. The frequency of the action potentials that are being transmitted is how things are coded. So let's say the cat steps on your toe and there's maybe 2 impulses that come by per second. The horse would make it 10 impulses come by per second, per unit time. So how do we encode for intensity of the stimulus? The answer, the frequency of action potentials. Frequency is the number per unit time. The more frequency of the action potentials, that tells the brain the larger the stimulus, because the amplitude, the height of the action potential, never changes on any axon. Okay, so then I thought, I'm going to show you guys changes in frequency. On the left here, we have one action potential shown in a certain time. Here are 5. That's how the nervous system does it. Increase in frequency of action potentials, not change in amplitude on any given axon. Of course, different axons would have different amplitudes, but on any given axon, the height of the action potential does not change. Good enough for that.